Good day, students. Today, we shall look into the different techniques used to obtain interference of light. Here on the screen, we see a beautiful image of the peacock feather. The vibrant colors of blue and green and hues of yellow are achieved due to the interference of light on the nanoscale structures present on the feathers. So, in nature, we have a lot to learn. Now, we know that to obtain an interference pattern, we need coherent waves to interfere to produce interference patterns. Now, this interference can be created by two techniques. It can be created by division of wavefront. In this, the wavefront from a common source is divided into two or more wavefronts by using mirrors or biprisms or lenses. So we have a common wavefront and that gets divided into two or more wavefronts. Now the second technique to create interference is by division of amplitude. Here we have the amplitude of the incident beam to be divided into two or more parts, and this is achieved by partial reflection or refraction. Okay. Now in interference of light by division of wavefront, let me further explain. Here we have the wavefront from a common source to be divided into two or more wavefronts by employing mirrors, biprisms or lenses. Okay, so usually we have a point source, and from a point source the emerging wavefronts will be spherical in nature. And if this point source is kept a bit far away, these spherical wavefronts then, after traveling a distance, a particular distance, they tend to become planar wavefronts. Okay, so these wavefronts, by making use of mirrors or biprisms or lenses, can be divided into two or more wavefronts. So the resultant wavefronts are achieved from a common source. So all the wavefronts will be identical in nature. Hence, these wavefronts are coherent. These waves are coherent and they interfere to produce interference patterns. Here are some of the techniques that are used to produce interference of light by division of wavefront. They are Young's double slit experiment, Fresnel's double mirror experiment, Fresnel's biprism experiment, and Lloyd's single mirror experiment. Now, to produce the interference of light by division of amplitude, here the amplitude of a beam is divided into two or more parts. It is achieved either by partial reflection or refraction, making use of beam splitters and mirrors. Okay, so single beam, it is divided into two. Its intensity is divided or its amplitude is divided. Okay, so the resultant beams, since they are achieved from the single incident beam, they are coherent beams, and when they are made to interfere, we get an interference pattern. Okay, so this is achieved in experiments shown here as the thin film experiments or in thin films, then the Newton's rings experiment, the Michelson's interferometer, Mach-Zehnder interferometer, Sagnac interferometer, Fabry-Peretz interferometer, etc. In this chapter, we will look into the interference of light by division of amplitude in thin films, Newton's rings, air wedge, and just see what is Michelson's interferometer. Now, let me show you how the division of wavefront is achieved in Young's double slit experiment. So in this experiment, we have a source, a monochromatic source light. Okay, and we have two slits placed in front of it, S1 and S2, a double slit is placed, and they are at a distance small d apart, and we have a screen placed capital D, a longer distance apart from the double slit. Okay, so this is the basic setup. Now, when the source is kept at a longer distance away from the double slit, we assume planar waves to be emerging from the source, and they fall upon the double slit. So when a single wavefront falls on a double slit, each slit produces its independent set of secondary wavelets. Okay, so secondary wavelets are emerging from both the slits, and after a finite distance they start to interfere. Okay, so while they are interfering, the crest of the blue set of waves may interfere with the trough of the red set of waves. Okay, the colors are just given to represent waves from two different slits. Okay, and so we can see that all these wavefronts are interfering, and if we place the screen there, we will see an interference pattern of alternate bright and dark fringes. The fringes will be equidistant from each other. Okay, so this is achieved in Young's double slit experiment. A single wavefront is divided into two wavefronts, two sets of wavefronts, and they are made to interfere to get this interference pattern. So let us just summarize it. The technique used in this experiment is interference by division of wavefront, and the apparatus required is a source, a monochromatic source, a double slit, and a screen or detector. Detector can be a camera. Now, what is the nature of the fringes? We obtain alternate bright and dark fringes of equal fringe width. And the expression for fringe width is given as beta is equal to lambda capital D divided by small d, where lambda is the wavelength of source light, capital D is the distance between the slit and the screen, and small d is the distance between the double slits. And here this equation is of importance. You have to keep this in mind. Well, this experiment was the first successful experiment to explain the interference of light by wave theory. But people were a bit confused because they doubted whether the interference is due to the slit nature or due to the bending of light through the slits. So they weren't convinced of the idea of division of wavefront. So it was Fresnel who devised another type of experiments, two other types of experiments to prove that interference is due to the division of wavefront. So in his next experiment, he used the Fresnel's double mirror experiment. And what is its setup? Let us see it. Here we have a source, a monochromatic source, and we have two mirrors that are aligned parallelly. Okay, so we have two mirrors, M1O and OM2. They are aligned along the same line. Okay, so they act as a single mirror now. Okay, and we have a screen. So this is a basic setup. And what happens here is light from the source will fall upon these mirrors and get reflected, obeying the laws of reflection. I is equal to R. So they get reflected towards the screen. Okay. So if I am looking from the screen, what I see is I happen to see a source in the mirror, right? If I'm standing in the position of the screen and look into the mirror, I will be seeing one source light. Okay. Now what Fresnel did was he tilted the second mirror by an angle theta. It is a small angle. Okay. So he tilted one of the mirrors by an angle theta, OM2 is tilted by theta. And what happens here is the beam reflected from the first mirror remains as such. It is shown by the blue lines. But rays reflected from the second mirror, they are shifted. Okay, see, they are represented by the red lines, and these beams are shifted into the reflection from the first mirror. So here in the region BC, we see that both the waves are interfering with each other, and in this region we get an interference pattern, and the nature of the pattern is that we have alternate bright and dark regions of equal fringe width. Okay. Now in this experiment, what happens is if we look from the screen into the mirrors, I'm just backtracking each ray. First, let us backtrack the blue rays. So what happens is they meet at a point here, and that happens to be the position of the first virtual source S1. Okay, and let me backtrack the red rays, and they meet at a point which happens to be the position of the second virtual source S2. Okay, so when we look from the screen into the mirror, we see two sources actually. Now by geometry, the actual source S, virtual sources S1 and S2 will all lie on the circumference of a circle whose center is at O. And if the tilt produced by the mirror is theta, the angle between the two virtual sources will be 2 theta. Okay. Now let the distance from the center of the circle O to the sources be small a, and the distance from the center of the circle O to the screen be small b. Okay. Then we have the distance between O and source to be a, b to be the distance between O and screen. Hence, capital D is given as distance between the source and the screen, and it is obtained as a plus b. And small distance is the distance between the virtual sources. Here, these virtual sources are lying on the circle, right? So I can say that the small d is actually arc S1, S2. Okay. So by geometry, I can write arc S1, S2 is equal to radius of the circle into angle made by the arc. That is small a times 2 theta. So let's sum up this experiment. In Fresnel's double mirror experiment, the technique used to produce interference is interference by division of wavefront. Here, the apparatus used are a source light, a monochromatic source light, Fresnel's double mirror, a screen or detector. Now, the nature of the fringes obtained are that they are alternate bright and dark fringes of equal fringe width. The expression for fringe width beta is lambda capital D by D, where lambda is the wavelength of source light. Capital D is the distance between source and screen, that is A plus B. And small d is the distance between the sources, given as A into 2 theta. Hence, the expression for fringe width beta becomes lambda into A plus B divided by 2A theta. We have rewritten the expression beta in these terms because while setting up the experiment, we can only have values of A, B and theta, right? We cannot directly measure capital D or small d. Okay, so hence we have rewritten the fringe width beta in terms of A, B and theta that we assign in the experiment. These two expressions are of importance. Now the next experiment that Fresnel devised was Fresnel's Biprism experiment, and in that he used Fresnel's Biprism. Biprism is actually a combination of two right-angled prisms as shown here. Okay, and their refracting edge is having an angle of 30 minutes. Refracting edge means these corners. Its angle, the refracting angle is 30 minutes. Now, if we combine these two prisms together, we get a single biprism. Okay, and the obtuse angle of this biprism is, the obtuse angle is this angle. Obtuse angle of this biprism is, yes, 179 degrees. So you should try to imagine such a prism. It is almost similar to a plain glass plate. Okay, one side is plane and the other side is having an obtuse angle of 179 degrees. Okay, so this is a Fresnel's biprism. What he did in this experiment was he placed a monochromatic source light in front of this biprism, and light from it was allowed to pass through a slit. Okay, the slit makes the beam narrow. Now, he placed a screen after the biprism. So this is the basic setup of this experiment. Now, when light passes through the slit and falls on the biprism, light falls on two sets of refracting surfaces, right? Light falls on the upper refracting surface and on the lower refracting surface. So light from the upper refracting surface refracts in this manner, represented by the blue rays. And light from the lower refracting surface refracts in this manner, represented by the red rays. Okay, so on the screen, we have these points. These two sets of rays, they interfere in the region BC and they produce an interference pattern in the region BC. Okay, again, the nature of the interference pattern is that they are alternate bright and dark regions of equal fringe width. Now, if you backtrack these rays, we can see that the blue rays meet at a point just above the source to form a virtual source S1. And backtracking the red rays, we can see that they meet at a point below the source to form the virtual source S2. Okay, so the peculiarity is that all these, the actual source S and the two virtual sources will all lie on a same line, on a same plane. And the distance between the virtual sources will be small d, and distance between the slit and the screen will be capital D. We actually use this experiment to calculate the wavelength of a source light. If we have a source of unknown wavelength and we need to find its wavelength, we can use this experiment to calculate the wavelength of source light used. So in that experiment, Fresnel's biprism experiment to measure wavelength of source light, the setup is as shown. The basic setup is as shown. So we have included two convex lenses in this experiment, and our screen can be eyepiece, that is an eyepiece that can be movable in the micrometer range, or it can be a camera. Okay, so this is to record the fringes or view the fringes. The eyepiece is used to view the fringes, or the camera can be used to record the fringes. So this is the actual setup. This is the monochromatic source light, a laser source. Here, a laser is all highly directional and highly monochromatic. So we need not use a slit to make the source narrow. and this beam is focused using a lens upon the biprism. This is the lens, and this holder holds the biprism. Okay, and the interference pattern can be viewed faintly on this screen. Now in this experiment, we make use of another lens, convex lens, as shown here. And all these components are moved along an optical bench or optical rail. It is a rod along which all these components are shifted. So for this experiment, first we need an optical bench that is leveled. So its leveling screws are initially leveled and made exactly horizontal. On these, we place several holders or uprights. And on the first holder, we place our monochromatic source light. On the next holder, we place a convex lens. This is used to focus the light into the next component, the slit. Now, the slit makes the beam very narrow. It allows only a small beam to pass through it. Now, light passing through the slit is made to fall on a biprism. The slit is actually placed in a vertical manner. So we have a vertical slit. Okay. And the biprism is arranged such that its edge is vertical. Okay. So the slit and the edge of the biprism should be aligned exactly parallel to each other. So these adjustments are manually done. The edge of the biprism is aligned parallelly to the slit, and they are both aligned in a vertical direction. Now the next component is, if these are aligned, we will be able to see fringes here. Okay, so to see the fringes, we will use either an eyepiece or a screen or a camera. Okay, so here in this experiment, we are using an eyepiece. Here, the first parameter that we measure is capital D. It is the distance from the slit to the screen. Now to begin this experiment, the eyepiece is first placed near to the biprism. Okay. And then the biprism is shifted in order to get two clear images of slits. We get the images of two slits in the eyepiece. So then we can fix the position of the biprism when we obtain two clear images of slits. Okay. Now next what we do is we move the eyepiece further away from the biprism, okay, until we get the pattern of fringes. Once you view the fringes, as you move away from the biprism, the fringes only appear to magnify. Okay. If they appear to shift laterally, if they appear to shift towards the left or the right, it is because the edge of the biprism is not aligned parallel to the slit. So during the initial setup of the experiment, I had mentioned that the edge of the biprism should be aligned exactly parallel to the vertical slit. If it is not so, here while moving the micrometer away from the biprism, you may observe the fringes to move towards the right or left. That is, it may have a lateral shift of right or left shift. Okay, so if they show a lateral shift, we can here adjust the edge of the biprism to make it vertical, and again verify whether it shows a lateral shift in the micrometer eyepiece. Once you have obtained an interference pattern without lateral shift, there you can measure the fringe width. So you will see a pattern as such. In the eyepiece, we have a scale that can be used to measure the distances. Okay, we have the micrometer scale. And in the pattern observed, we can select any one of the fringe to be the initial 0th fringe. Okay. So here we are going to calculate the distance for 15 fringes. So we need to calculate the width of these 15 fringes. So this is the 0th fringe that I have selected. So that the reading at that position will be x0, and after counting 15 fringes, the reading at that position will be x15. Hence, the fringe width beta is obtained as width of n fringes divided by n. Here I have taken width of 15 fringes divided by 15. That is, beta is equal to xn minus x0 divided by n. Here we have taken x15 minus x0 divided by 15. Now, in the second part of the experiment, we are going to calculate the value of small d. We are going to calculate the distance between the two virtual sources. For that, we make use of the second lens. Okay. So initially, this lens is placed near the biprism, and when it is adjusted to and fro near the biprism, we get two slits in the eyepiece, and this image is magnified. That is, we have two slits that are very much apart from each other. Okay, so in this position, the distance between these two virtual sources is measured in the eyepiece as d1. Okay, and the distance from the slit to the second lens is measured as u, and the distance from the lens to the eyepiece is measured as v. Okay. Here, when the lens is at this first position, the magnification of the image is given as height of the image divided by height of the object, which is equal to distance towards the image divided by distance towards the object. And here it is given as d1 by d is equal to v by u. Let this be the first equation. Okay. Now, the lens is then taken from this position to the second point. The second point is near to the eyepiece. It is placed nearer to the eyepiece. And when it is adjusted at that position, okay, we will get an image of two slits. Okay. And it is a diminished image of the two virtual slits. That is, the slits appear to be very much closer to each other. In the eyepiece, I can measure the distance between the two slits, and it is measured as d2. And here the distance from the slit to the lens is measured as b, and distance from the lens to the eyepiece is measured as u. Here you would have noticed that earlier the object distance was u and image distance was v. Okay. Now, by property of the second position, okay, these two positions are actually called conjugate positions. So in conjugate positions, what happens is, in the first position, if object distance is u and image distance is v, in the second position, these distances are just interchanged. That is, in the second position, object distance becomes v and image distance becomes u. So that is what we are seeing here. Okay. So at this position, when lens is at the second position, magnification can be written as d2 by d is equal to u by v. Okay. In this expression, the height of the image is d2, height of the object is small d. We cannot actually measure that. Okay. It is the distance between the two virtual sources small d. And the conjugate positions, we have the numerator, it is the distance to the image as u, and in the denominator is distance to the object as v. Okay. Now, multiplying these two equations, what happens? We get d1 d2 by d square is equal to 1. Great. So here we can derive the relation for small d as square root of d1 d2. Okay, and this equation is of importance. In this experiment, we can measure d1 and d2, right? So taking square root of these two terms, square root of d1 into d2, we will get the value for small d. Okay. So in this experiment, we have used the technique of interference by division of wavefront, and the apparatus required are a monochromatic source, a slit, Fresnels Biprism, two convex lenses, and a screen or detector. Detectors that can be used are an eyepiece or a camera. And the nature of fringes obtained are that they are alternate bright and dark fringes of equal fringe width. The expression for fringe width is beta is equal to lambda capital D divided by small d, where lambda is the wavelength of source light. Capital D is the distance between the slit and detector. Here it is U plus V. Okay, U and V are directly measured. And small d is the distance between the two virtual sources. We can measure it by calculating the square root of d1 into d2. We also have another expression for small d. If alpha, that is the refracting angle of the biprism, is given, okay, we can use another expression to calculate small d, and that is d small d is equal to 2a times mu minus 1 into alpha, where a is the distance between slit and the biprism. We can directly measure it from that optical bench. Mu is the refractive index of the biprism, and alpha is the refracting angle of the biprism. Now, when the Fresnels Biprism experiment is viewed under a monochromatic light, the fringe pattern obtained is as such. So we have used a monochromatic source light of red color. So we get a pattern of red fringes as such. Here, the fringes are of the same color. We can measure fringe width from it, but we cannot locate the central fringe, or the 0th order fringe cannot be located from this pattern. So what can be done? Now, when we use white light in Fresnel's biprism experiment, we get a pattern as such. Okay, here we have the central white fringe, which is flanked on both sides by colored fringes. And the central white fringe gives the position of the 0th fringe, or the 0 order fringe is the position of the central white fringe. But the disadvantage of this pattern is that it cannot be used to measure the fringe width. The fringe widths are not constant, it is colored, so we will be confused on taking measurements from it, or the detector will be confused on taking measures from it. So we use white light only to locate the 0th order fringe, or the center of the interference pattern. Now, what do we actually observe in interference of white light? Now, considering white light, we have a spectrum of different colors, of different wavelengths, right? So for different colors, we have different wavelengths. And refractive index mu is dependent on wavelength. Okay, so each color, when it passes through the biprism, it refracts differently, and it will interfere differently, and in the interference pattern we thus get fringes of different colors. So the pattern obtained is as such. Here in this biprism experiment with white light, you should take notice of this pattern. Let us observe this pattern. Here we have the central bright fringe, it is white in color. Okay. And on the first fringe on both sides, we have a fringe of inner red edge and outer violet edge. We have a relation for fringe width and wavelength. Fringe width beta is directly proportional to wavelength lambda. Here, if we use only blue color to interfere, the pattern obtained is as such. Okay, here we can directly measure the fringe width. Okay, the fringes seem to be a lot more closer. But if we use a monochromatic source light which is red in color, we again see fringes, but the fringes are further apart from each other, right? The fringes in the blue spectrum are closer, whereas the fringes in the red spectrum are farther away from each other. Okay. This is because of this relation beta is proportional to lambda. That is, fringe width for the blue wavelength is smaller and fringe width for the red wavelength is larger. So at the center, where the path difference from all the rays is 0, all colors will interfere constructively, giving white fringe. Okay. Now on both sides of this white fringe, which color has its dark fringe to come first? Violet or red? It is violet, right? In the spectrum, you can see that the first dark fringe of violet comes earlier, and the first dark fringe of red comes later. Okay, so when the first dark fringe of violet is present, the bright fringe of red is still existing. Okay, so here in this region, when violet becomes absent, red is still sufficiently available here. Hence, the inner fringe appears to be red in color. Okay, so on either side of the central white fringe, the first dark fringe of violet comes first, where there is still sufficient light from the bright fringe of red. Hence, the inner edge appears red. Now, when the dark fringe of red is present in these 2 points, we get the first bright fringe of violet to come. Okay, in the center we have the 0th order fringe. On either sides we have the first order bright fringe of violet to come. Okay, so here when red is absent, violet is having a maxima region. So in this fringe we get the outer edge to be violet. Okay. At larger distance from the center, that is after 10 or 12 fringes from the center, all these colors, they overlap and uniform illumination will be seen there. Okay. So nature has given us quite a lot of examples where we can learn about the interference of light. We have seen the interference of light by division of wavelength in 3 different experiments: Young's double slit experiment, Fresnel's double mirror experiment, and Fresnel's biprism experiment today. Okay, thank you.